Welcome. My name is Kirk Shoop, and I'm going to be talking about algorithms for values distributed in time. The slides for this talk are live. They're committed to GitHub, and that's a live website. The slides are interactive, so if you want to follow along, pull them up and play with them. So about me, I love code. This isn't my natural habitat, standing up and talking to people. I'd rather be with my back to a wall and a bevy of screens in front of me. But I care about code, and I care about things that make it hard to make errors, to check in errors. And so I've done a variety of utilities over time, and this is the one I've been working on for the last couple of years. My team has a meeting every week. My manager goes and asks us to give a number between 1 and 10 to describe how good our week was. And the weeks that I code, I have a high number, and the weeks that I don't, I have a low number. So I work at Microsoft. I was going to school in Seattle in college, and my roommate at the time was a CS major, and I was not, and his homework was fun. And so I went and took a class in Windows programming, and a couple of people from Microsoft were also taking the class, and they insisted, based on the class, that I submit a resume, and I became an intern. And then they renewed the internship, and I was in school and interning until they couldn't do that anymore, and then I became a contractor, and finally, eventually succumbed and became an employee. And that was in 2001, so, but my internship started in '93, so I have been in a couple of other companies in between, but I've spent the majority of my life at Microsoft. So the goal here is to talk about algorithms that are additive to what we're already defining in the standard. Things like STL and range v3 and parallel STL, they all deal with values distributed in space, vectors, lists, even generators. These are things that are already available before you call the algorithm. And the distribution of the values is in space. And they do an incredibly good job at that. Parallel, in addition, has the trade-off of trying to consume as many resources on the machine as possible to get the processing done as quickly as possible. Whereas the algorithms I'm going to discuss are dealing with values distributed in time. You may not have them all yet. And its goal is to be extremely efficient while it's waiting for the next value to arrive, and then process it with a fairly low latency. And so these are additive, not overlapping to what we have already. Another goal is to scan through some fairly dense slides without trying to completely understand all the code or all of the concepts, and then at the end go back and talk about questions and hopefully get a little more depth. And then finally, the actual purpose of the bulk of the slides is to demonstrate how particular algorithms that are useful in this domain impose certain requirements, just like the Iterator types. These algorithms impose certain requirements on a abstraction that will allow them to be written, that will allow them to function. So examples of code using values distributed in time. I assume you've probably seen Sean Parent's talk about using algorithms over raw for loops. I kind of think the same thing's going to eventually apply to raw callbacks or raw futures. You're essentially going to get to this point where you actually want to see people using algorithms instead of re-implementing them every time they add a callback. And then the other interesting Formative talk is Eric Niebler's for the Range v3 library, where you'll hopefully, if you've seen that, some of these expressions will start to look familiar in the way that they compose algorithms. So this slide deck, like I said, is fairly interactive. I've compiled my C++ code with Emscripten to JavaScript, and it runs live in the slides on transitions. So the expression on the left is actually running on the right, and the output is coming out on the right. This is a fairly simple expression that is just taking the first three even numbers from integer values distributed every second, arriving every second. And it actually delayed them. The delay is highlighted in the algorithm. So this diagram shows what delay does every time that the source emitted at 1 a second an integer. The delay made it actually wait another second before it actually arrived, before it was actually emitted. This is another example. This one is actually, I haven't seen this at the conference yet. There's actually a co-await syntax for the for statement. And what it imposes is that begin has to return an awaitable, and it will be co-awaited of the range on the right-hand side of the colon. And plus iterator also has to return an awaitable, and it will be awaited. And so what you end up with is the ability, this is actually the modern CPP library. This is code that has been running in the modern CPP library, where pointer presses from the GUI library, from WinRT, are actually being emitted by the pointer pressed generator, async generator, co-generator. And then you can actually apply these, using the pipe operator, apply a transform that extracts the position from each pointer pressed, and then a filter that only passes on the position if there's no shape there on screen at that point. So it can't select it, it can't find a shape, and then it'll just add one since it can't find one. And then that used copy if or filter, which just takes an input stream and based on the lambda passed in, decides whether or not the value should actually be passed to the output. This is the same library. It's using for co-await, it's using pointer pressed, it's using pointer moved and pointer released, and this actually only emits objects that are selected, and it emits the move events from the pointer while the mouse is down. And so this, with zero state in your class, this single function will let you click and move visuals around on a canvas. And it just uses the same standard algorithms. This one introduces merge, where it's merging all of those events, all those streams together of move events, and this allows interleaving between things that are distributed in time, different sources distributed in time. This is the same thing, but using a different library that's actually hooked up with the Emscripten. And so it will actually count the number of moves that were emitted during a drag. And that used take until. That's how the pointer up terminates the previous stream of moves. So we only subscribe to the moves while the pointer's down, and the way we know to stop listening to moves is when the pointer released occurs. And so take until implements that. It waits until the second stream emits its first value, and then it stops taking additional values in the output. This is using it on an async source of bytes to extract packets. And so the packets in this case are delimited by carriage return. And so this is just an application of a few algorithms on the async source of bytes to extract out messages. And so you can use the same algorithms on any async source of values, be they network or HTTP requests, which I use all the time in JavaScript. The same libraries are available in a lot of different languages. And so my job has me using JavaScript these days and a whole bunch, like hundreds and hundreds of coordinated HTTP requests from the client browser. And so I just use RX expressions like this to coordinate all of those so that they're orchestrated correctly. This is an example of using an HTTP request in C++. Again, it's hooked through to the Mscripton library. So the browser actually made an HTTP request for the README MD for RxCpp on GitHub, and then displayed the first line. And it's fairly quick, even in JavaScript. So that used scan, which is like reduce, but instead of only emitting one value at the end, it emits each new value as it's produced. So the Lambda still runs there's still an accumulator variable, but that accumulator is emitted every time it's updated. And this allows a lot of common patterns around making sure that you can have a whole bunch of streams going into this scan, and each of them is updating the accumulator, which can actually be, say, the model for an application or some other data source. And now you get a notification every time as an output. You get a notification every time that data source is updated. And so you can do things like rendering off of that or any other sort of data processing. So, of course, the common reasons why you want algorithms as opposed to raw code is because you can reduce them in a generic way and document exactly how they behave. You can end up having people maintain them actively for a few people maintain them actively for a huge number of people, so they end up being stable and optimized. And because of all the time that's gone into reducing their scope to a particular doing one thing well, they tend to be fairly descriptive when you compose them, so that you can actually kind of read code a little bit better when you're consuming algorithms, assembling algorithms together than if you're just looking at raw code. So algorithms operate on sequences of values. And we can deliver those in a variety of ways. In space, you can have a vector, you can have an array, you can have a generator. Every time you call it, it immediately returns you the next value in the sequence. These are all expressions of data that are distributed in space. You can also have things distributed in time, like mouse move events and network packets. That's what this talk is about. So reactive extensions is a set of algorithms that has been implemented across several languages. It's used in production at Netflix and at Microsoft. Both in at Netflix, they use RxJava and they use RxJS, whether they're client or server, depending. So there's implementations for many languages, and so this is just for the RxCpp library that I've been working on for a couple of years. These are the algorithms that have been implemented. So much like the STL, this ends up being a fairly extensive set of algorithms. And it's not done yet, but it's actually in pretty good shape. It's built for CPP11. It runs, it can be compiled by 2013 Visual Studio, 2015 Visual Studio, Clang, and GCC. And all of these are tested every time the GitHub is updated. So let's talk about algorithms to help define what the shape of an abstraction to support them requires. You have an algorithm like copyIf. It's just a filter. It's deciding whether or not to pass something along. That needs to selectively pass onto the next handler to the output stream. Last or default needs to be able to select needs to know when the source is complete, when it's not going to receive any more values, so it can return the last value that it had stored. Take needs to be able to stop the source even if it isn't done yet. Delay needs to be able to schedule a function that will be called later rather than blocking the source, immediately return to the source, but schedule a function that will be called later to emit the actual value. Resume error needs to be able to have the error delivered to it in such a way that it can instead return a new stream whose values will continue the old stream instead of stopping it. So in the course of building this talk, I ended up building a proof of concept library that I'm calling RxCppV3 that's C++14 and has only been tried on Clang. So it's significantly different from the more robust V2. But it's useful for these slides. Things look a little better. So your simplest features to support something like copyIf is you've got to have a source, an observable, that you can bind to an observer that can receive the values as they are produced. You have to be able to lift. You have to be able to take an observer, and in order to build an algorithm, you have to have, you implement an algorithm by implementing lift. And so it takes an observer, it adds its own functionality in front of that observer and returns a new observer. And so you can wrap observers in order to provide additional functionality implementations of algorithms. And so you'll see that the source ints makes an observable and just has a for loop that calls next over and over again. And what it got passed was the observer. And then you'll see copyIf is an implementation of a lifter, and it makes a new observer that just calls the old observer if the predicate's true. And auto lambdas make these much easier, like C++14 make these much easier to show on a slide than the equivalent functor objects that I had in RxCppV2. Yes?
I'm curious why the observer API is useful instead of just raw callables. I would think an operator friend would get us there too.
Yeah, so this is just copyIf. Oh yes, the question was, or the comment was that, why couldn't you just use a straight operator callable to represent the observer? The observer will need some more methods on it. So this turns out to be pretty effective. You can insert the copyIf after the ints and print the results to cout, and it all runs. But we want to support other algorithms than copyIf. So last or default, remember it needed to allow us to know when it was complete and store the value until then. So we need to know when it's complete. So now the observer needs a complete method. And when we make the lifter, we also make a subscriber, and then inside of that an observer. And when we're getting a value, we store it in some state that we allocated. And when the complete arrives, we forward the stored state and then forward the complete. And so that's the implementation of last or default. So that was 100,000 integer values going through last or default, and we only omitted the last one that went through. So that's it for that algorithm. On to the next, take. The take algorithm requires you to be able to cancel. You have to stop the source early before it's done. And it also needs to keep state to figure out when it's time to cancel. So the types of features that are needed for asynchronous lifetime and cancellation. So in order to store state, you have to be able to allocate state that's scoped to the lifetime of the asynchronous expression, not scoped to a block in C++. And so you need your destructors to run when the expression is complete, canceled, or errored, and not before. And so you end up having to provide something that allows you to do an equivalent of make shared that's scoped to the asynchronous lifetime. And you have to be able to nest these lifetimes. There are various algorithms that need to be able to nest them. And you have to be able to register with that to a function that will get called back on cancellation so that you can do work in your algorithm to actually perform the shutdown. And then you have to be able to call on that lifetime the trigger function that actually shuts down everything. And what you'll find is that if you've got an expression and there's something in the middle of that expression, like a take, everything above that expression is going to be canceled, and everything below that expression is going to be completed. And so the cancellation goes up and stops the source, and then the completions go down to the tail of the expression. So a subscription represents lifetime in this library. And you have on the right all of these functions that allow you to use the pipe operator to bind all of these things together so that you can late bind your lifetime, and you can late bind your observer. And with the adapter, you now have the choice for each algorithm, whether you're going to build a lifter that goes from subscriber to subscriber, or whether you're going to build an adapter that goes from observable to observable. There are some algorithms that actually may require going from observable to observable. Yeah, so this gives you all of the options for signaling the stop, for registering for when it's stopped, for nesting other lifetimes, and for creating state that's scoped to this lifetime. So take ends up being an adapter where you make an observable, and then once you've been passed a context to your subscriber, then you're able to make the state, make your own observer that will early call complete. Now, there is underlying in this library, there is contract enforcement. So every time a complete is called in the library, it knows about the lifetime of that scope. And so it will forward the complete and then call the unsubscribe, the stop the lifetime. And by doing that, I don't have to explicitly stop the lifetime here. I just call complete and it implicitly stops the lifetime as well. So we early call complete, and that will stop the source and complete the targets, the receivers, observers. So that worked. We were going from 0 to 9, but we only took 3 values and then we stopped. So we also have to support failure. And so we had to add an error method to the observer that will allow us to pass errors on down the chain from their point of occurrence. So again, errors, just like complete, will force cancellation. So if you call an error, the error will be passed down the chain, but the cancellation will go up the chain and stop the source. Right, so this just used the existing copy if algorithm, but it passed a predicate that always throws, so no values come out. Take never really came into the picture at all, and the error went down through to the print to cout and the what string was printed out, which was always throw. And then the whole thing shut down. So we also need to be able to schedule functions to be called later. And that means that we need something like an executor or a scheduler or a strand. Here it's called strand. You can defer at a time point an observer. So the observer next will be called at time point. Note for later that we also have a member function now, not a static function now. The context binds it binds some state to a lifetime for the subscription for the expression, and a scheduler for the expression. And so then you can bind those in using starters and subscribers, bind those contexts in. So here we can delay using the makeStrand scheduler so that what comes out 1,500 milliseconds after it was emitted by the interval at the top, which was only emitting every second to begin with. So we get this pattern of produces and consumes, and they're fairly stable. They pretty much always come out the same way. Well, they always come out the same way. It's kind of important. So the strand has to be a FIFO queue for time t. That means that if you add a whole bunch of things that are supposed to be executed at the same time, they have to be FIFO at that time. Yeah. So we also want to support testing because it takes a little while to run this. It's a bit too slow. We want to be able to test these things in time without actually consuming that much time. So you end up with a virtual clock that again has a member now, but also it now has a version of now that will let you reset the clock to a new time. So you actually have virtual time, you're controlling time rather than just reading it from the underlying system. So, and then you have to have a loop scheduler that can make strands based on this virtual time. And when you use it, you can either step through time, or you can just run it through all time, through the whole queue. Then you need to be able to produce streams and record them in order to do the testing. And so this just lets you associate a time and a value, or a time and an error, or complete and call it a marble. And you can use hot and cold to actually produce observables from a vector of marbles. So we're actually making marbles values in space, and then producing observables on them. And as values in space, they're actually associated with the time that they should be emitted. And so what actually ends up happening when you test using this is that test loop will just pick the top off the queue, set the virtual time to match the time on the top of the queue, and then call it. So the result is that same expression happens instantaneously instead of taking so long, but it still thinks that it happened over 4.5 seconds. And the way that that expression was done was that you actually supplied the list of nexts with the time that it should happen and the value that it should produce. And then you recorded them using on.record. At various points you can record, and then on.test terminates the test, and then you just run the loop in order to do it. So you can actually have multiple of these expressions set up and then run the loop, and they will all run in order. So for instance, there they are side by side, the one using the regular scheduler and the one using the test scheduler. And it ends up being quite a bit faster for testing. So this is what that looks like. On the left, you have the way that you recorded the test result, and then on the right, you have the way that you assert. So you can actually then create a vector of values, of marble values that you expected to be emitted, and you'll see that those are different than the marble values that were passed in. And then you can just check whether the marbles that were emitted are equal to the expected, and then you print either the succeeded, which we got from the previous, or you get failed, which we'll get from the next. So I passed in a different value for take in this one, which doesn't match what the expected sequence expected. And so what we actually get is the failure, and then you actually can see in the printout that we only got one of the 3 values and that completion happened way too early. And so we failed. So the requirements that fell out of these algorithms are that we have to have the sense of knowing when the next value occurs, we need to know when completion occurs, and we need to know when an error occurs. We need to know the lifetime of an expression, have something that represents that lifetime that is unbound to the compiler's sense of lifetime. And then we have to be able to allocate things to that lifetime for state within the algorithms. We need to be able to cancel an in-progress expression, and we need to be able to schedule functions within it to occur later. And those functions need to be FIFO for time t, for a particular time t. We need virtual time in order to do testing, but it's also useful for things like video decoders or anything else where you want to actually scrub through time in your expressions. So I also did some work this year, and you saw some of it at the top. And of course, these are only running on the Visual Studio compiler right now, 2015, because they used the co-await proposal. And so I haven't actually been able to get them running in Emscripten yet, but Clang's coming, and then hopefully they'll run in Emscripten as well as the rest. But this is what transform looks like if you have a co-value generator. You just co-await your source, and your selector gets called, and then that result gets yielded. And so this is the whole implementation of that function, of that algorithm. And concat is similar. You can have nested for co-awaits, and those naturally express concat. These are the easy ones. After a few false starts, I went to do merge, and I've omitted the 200 lines of code that wouldn't fit on the slide to show just the kind of surface that invokes all of that 200 lines of code. Merge turns out to be pretty difficult when you're dealing with co-await, because co-await naturally uses code rewriting to naturally serialize your code, your async code. And so concat's very easy to express, and copyif is very easy to express, and transform, and a few others. But anything that's actually taking in multiple sources and wants to actually await all of them ends up being fairly complicated to achieve. Not impossible, and that's what libraries are for, but it's not as, like these are really compelling, why would you use anything else? And this is not so compelling. So if you, it ends up looking very similar. You end up using for co-await instead of passing lambdas into the end of an expression. You use the expression in a for co-await, and the body of your expression is where you do the work with the outputs. It ends up having a code generator that has begin returning an awaiter that will resolve to an iterator later, and then end just returns an iterator straight. The end iterator is simple, and then the iterator on the right, the ++ operator, has to return an inc awaiter. This is different. We're not awaiting a new iterator. We're awaiting the current iterator to be updated, because increment applies to this, not returns a new copy of a different iterator. And so there's two different awaiters involved, one for the begin and one for the ++. And the iterator awaiter, it looks fairly similar to any other awaiter. It returns the iterator on resume, and the inc awaiter returns a reference to the current iterator on resume once it's been updated. So I have run through this with great alacrity, too fast to actually get anything to sink in, precisely so that I can concat all the questions and have some discussion about async algorithms and expressions of them, whether they be transducers, which I haven't shown, or reactive extensions like push models, or co-await, which is a little more pull but kind of ambiguous that way. Yeah, open floor. Let's have a talk. Yes.
So this syntax seems to be pretty great for expressing chains, but DAGs seem to be pretty awkward, especially if they have any breadth. And also particularly if you depend on data that is both spatially and temporally distributed, such that you may depend on neighbor points or something that arrive at different times. Can you talk a little bit to how you would extend that to this?
Mm-hmm. Yeah, so the question was that it seems to work fairly well until you get into more of a DAG, directed acyclic graph. And I'm processing how I would respond to that. I believe that it just depends on the algorithms that you use or the algorithms that you build. The ones that are popping in my head that seem to apply to this are things that combine different sources and coordinate them. So you can have you can have the same source but with different filters to get different subsets of it or different views of it, and then you can combine all those with things like combine latest or zip or merge to get to combine them back again or to reduce them. There's reduce and scan. There's a variety of ways to kind of fork out into multiple sequences and then merge them back into a new sequence. So it doesn't feel like it would be any different than, say, using the range v3 library if all the data was in space, was already there, it should be the same sort of transforms to, sets of algorithms apply the same sorts of transforms in time as well. Because you can, each of these algorithms can have state. And so, for instance, combine latest is one of those algorithms that has a single value stored for every stream that was input. And only once there's a value for every input does it output essentially a tuple of all of them at that moment. And then every time any one of them changes from then on, it puts out the whole tuple again. And so there are various ways that you can reduce the types of combinations that you want into these simple algorithms, and then you can apply them. Yes?
I was wondering if you compared this framework to just kind of handwriting equivalent piece of code with the overhead, so lack of overhead.
Not strictly from a performance question or perspective. No. I have, oh, I'm sorry. The question was, have I compared this to handwritten code for performance? So in the V2 library that's more stable, I spent a lot of time getting performance compared to for loops. I don't think this is, that's a task for the range v3 library to actually, maximize the performance over a set of things. This is more of not necessarily taking a huge amount of data and reducing it very quickly. It's more of a coordination thing where you're trying to not have anything on the stack until there's a value to be processed, and then to kind of wake up and do everything that you need to do and then go back to sleep again. So you end up having things like mouse click events, so that on the message loop tick, you're getting some outputs, and then those are running through the functions. So I will talk a little bit about performance in the libraries that I've worked on. The goal is to kind of keep the zero abstraction as much as possible. Lifetime is the one that makes it non-zero. The lifetime and the scheduling are actually things that impose some virtual functions, so you can have queues of scheduled functions. Those have to be virtual functions. Everything else, the actual simple operators like transform and copyif and filter, those types of things, those are actually by default no virtual functions. Like when this expression tree is resolved, the compiler can see the whole thing and smash it down into one block of code. And so that usually ends up being pretty simple. But as soon as you start putting in the interesting stuff like merging, which requires some scheduling, delays, observe on, which is pretty useful in these expressions, because I don't know if any of you saw the WinRT routine talk, but you can do the await resume background to switch threads in the middle of a function. Well, there's algorithms for that, observe on, in these libraries, and so you just put observe on and the make strand, and suddenly the rest of the expression's on a new thread, and then you put another observe on with a different scheduler, and you could be back on the UI thread or whatever you wanted to return to. And so those types of things, when you introduce them, introduce overhead. But when you're just doing things that don't have any of that scheduling or lifetime issues, they just smash right down in the compiler.
For the data in space, we have the standard library of algorithm. And these algorithms, if you want to compose them, you can write a function that calls them in the order you want. Here you chose a syntax with the type operator. I am wondering whether it's just a design choice, or there is something more fundamental about the difference between time and space sequence.
So the question is whether there's something fundamental for you to the time-based sequence that made me choose the pipe operator. The V2 library of RxCpp, it primarily relied on a huge observable class with every single algorithm in it so that you could do dot method and have IntelliSense help and all that. Well, that was a huge recursive compiler nightmare. This really makes that go away, the pipe syntax, and it happens to match range v3, which is definitely working in space, so it's certainly nothing specific to time. But also, if you'll look on this slide at the 3 even, that's actually an operator definition. Like I just composed copy if, take 3, and delay, and now I have the first 3 even delayed by 1 second, and I can apply 3 even in the middle of any expression, and it will just, it's an operator now.
Have you done any predictive filtering so that you were looking at a sequence of events, data, and if something isn't there, or if the intervals are not right, then you can predict where it should have been, that kind of stuff?
So those sound like interesting operators to build. I mean, it sounds like maybe an interpolation algorithm or something.
Or averaging.
Oh, repeat the question.
Averaging
Sorry.
would be one method to do.
Averaging? The averaging method that's in the library is a reducer, so it actually produces an average at the end. You could certainly implement average with scan as well, so that every time there was an update to the average, it would be emitted immediately.
So it would be one indicator of data quality.
Yeah. Essentially, you know, the goal certainly of this talk is to talk about the right abstractions so that all of these algorithms are possible. And then they just have to be defined and written. Yes?
Have you ever dealt with streams in time where the timestamp is part of the stream? Like, for example, you measure something from a device, you get the timestamp from that device, but it arrives late there, because that like kind of complicates merge a lot.
Right, so have I ever dealt with streams that have the timestamps embedded in the message? So certainly the mouse events are things that often have the timestamps embedded, and how do they complicate merge? Well, merge is dealing in the domain of the stream, the input streams. So it's really dealing it with the time of arrival, not the time of the timestamp. But you can build, using these algorithms, you can build things that will say reorder the incoming streams. But you have to have some sort of, your algorithm has to have some sort of limit, timeout, if you will, to say, you know, I'm not going to remember any more, I'm going to remember only 6 values and make sure that they come out in the right order. But if something is more late than that, or I'm only going to remember, you know, 50 milliseconds of values as inputs to the algorithm, you set these conditions, you know, so that you don't end up just queuing forever and never knowing when you can actually emit. You would have to basically impose some sort of delay if you want them to come out in order. And I don't know what other things you were thinking about as far as how you would want to deal with late values. Because merge would just deal with them as arrival, naturally. Yes?
So, first of all, greatest slides I've literally ever seen. Played around with them the whole time until my battery ran out.
Cool, thank you.
Yeah, I can't check now because my battery ran out. But do you have a branch, and how is that to feed the rest of the chain or DAG? And then secondly, is this just not really designed for situations in which the DAG is too large to build all at once before you start flowing data into it?
So the question is, do I have any sort of branching, and you know, does this apply to, you know, in cases where the DAG is just extremely huge? This is really designed to coordinate events coming in over time. I don't know if the DAG you're thinking of is actually distributed in time or if it's actually a fixed entity.
It would be distributed. It would be distributed in time, but it
Okay.
would probably start relatively synchronously, and then asynchrony develops over the course of the computation.
I see. So you would start with a fairly synchronous amount of data, and then asynchrony would come in as things completed. This isn't really trying to update things in place. It's trying to deal with things arriving in time. So certainly as you were processing something, if you were reducing a whole bunch of things and had a whole bunch of reduced results that were arriving and you wanted to coordinate those, this is where this would kick in. It's really more about coordinating the things once they become async rather than processing them while they're still sync or static. But we do have, there's multicast. You can publish a source, and then you can observe that source as many times as you want. And they will all of the observers will get the same set of data, and then you can apply filters to each one so that each of them actually only sees a subset of the data. Or you can use the group by operator, and based on a key that you supply a function to calculate, it will create a new stream for every new key that it observes. And then each of those will essentially be filtered to only receiving values that match that key. And then, lots and lots of algorithms for switching. There's also switch on next. So if you have a set of streams where the streams themselves are being produced over time, then you can switch to only see values from the latest stream, or you can merge them, or you can concatenate them. So there turns out to be a whole lot of different algorithms that apply somewhat uniquely in this space. You know, they don't really have analogs because of the time domain in the RxCpp, in the range v3 library or STL or. Yes?
Do you build the computation graph lazily so that if the user does something stupid like a delay followed by a filter, you can just put the filter in front of the delay since it's mathematically identical, or do you do it just bind it up and do whatever they say?
That would be spectacular. Yes. Do I lazily construct the graph, or do I do it as the operators are invoked? So if I did it lazily, then I could reorder things and optimize things, even if the user wasn't making good choices. Definitely true. That would be wonderful. This is not an expression library in that sense. It doesn't record everything and then reduce it into the final result. That probably would be a very useful expression of this library, like a very useful library to have. This one very much just constructs each operator where you told it to be and pipes them together. Yes?
The choice of that pipe operator, when we ran before, did you see any increased compile times? Because I do remember Chandler talking at one point complaining as an implementer that they run out of ideas about how to optimize for that type of operator.
Yeah, so have I seen compile time issues with the pipe operator? I have seen compile time issues with this library, with all these libraries that I've tried. They definitely do strain the compiler because of all the types that are being generated and chained together into longer types. Like I said, for performance reasons, I was trying to keep virtual functions out. And so everything is actually just becoming this huge single type over time that the compiler can just smash down at the end. But it generated so many types to get there that it ends up being a bit stressful on the compiler. I've added I think most of the libraries, the virtual functions can be introduced at any point, just it's another operator, and you just pick the points where you want to kind of cut down the compiler work and you're willing to trade off the runtime cost, and you say, okay, make that an interface, make that an interface. Yeah, I guess I found just as many problems with the dot method which I really wanted to use because of IntelliSense. Oh, that's sad. I wanted to use the dot method so much, and I did so much work to make that work across all 4 compilers in V2 with all of the recursion problems, because the observable type has to exist before the algorithms are implemented, and it also has to contain all the algorithms that are implemented as methods. And other than that, I don't know how else you would. The other way is the transducer way, which is function composition, where you end up looking like Lisp. There's just tons and tons and tons of parentheses. Any other questions? Well, 5 minutes back for everyone. Thank you very much. I really appreciate it.